Alright, so in this lesson we're talking about 2D motion. And the nice thing about 2D motion is that we don't have to do a lot of changing when comparing it to 1D motion. We're just putting the two different dimensions, x and y, together. The one thing that's really important to remember is that the two directions do not have an effect on each other. So the x direction will not have an effect on the y direction. And that's really important as we move on when it comes to solving problems and getting stuff done. So the first thing we want to look at as we move along is vectors and scalars. And I know you did a lot of work in your summer packet that has to do with vectors and scalars, so I'm not going to spend a whole lot of time on it, but it is important to know the difference between the two. So a scalar is something that has a magnitude only, magnitude meaning number. So a scalar is something that is a distance, a speed, a time, a temperature, something like that. Something where you wouldn't necessarily say a direction that goes with it. So in this case, you wouldn't say like 34 degrees Celsius north. It just doesn't make sense. So again, scalar, no direction with it, and that's very, very important. You see, though, as we move on and we get to these vector things, that we have speed as a scalar, but velocity as a vector. And the big difference here is that vectors have a magnitude and a direction. All right, that direction becomes very, very, very important. And that's one of the things that differentiates speed from velocity is the fact that velocity has a direction, and you have to take that into account. You can never just forget about that direction when you're dealing with vectors. So it becomes very, very important. And you can describe those directions in many different ways. You can have them using the directions of the compass, north, south, east, west. You could have them just using angles, like on a coordinate plane, so 41 degrees, 340 degrees, whatever it may be, something like that. There's also another way that a lot of physics textbooks like to use, which is kind of a mixture between the compass directions and regular angles, so something like 50 degrees south of west. Right, so here we'd go to west, the west meaning 270 degrees, and then going down another 50 degrees from there. So that would give you something like 320 degrees. So lots of different ways to describe the direction in which a vector is pointing. So like we said, the direction is very important when it comes to vectors. And again, you have to take that into account. When we add them, we're going to use this thing called the tip to tail, meaning whatever order that we're asking them to be solved in or added, we're going to draw the first one, say A, we're going to draw it out, and then we're going to take the second vector, which may be called B, and put it on the tail of B onto the tip of A. And when we do that, we can then go through whatever order we're asked to do, and then when we want to find what the sum is, the total, we're going to draw the sum, or call the resultant, from the start of the first vector, so that the tail of the first vector, to the tip of the last vector. All right, and that final resulting vector that we get, the sum of them, we're going to call the resultant. When we do subtraction, the only difference we're making or performing is we are going to change the direction of whatever vector gets the minus sign. So if you have A minus B, that B is going to get the minus sign. That means it needs to flip its direction 180 degrees. And when we do that, it goes from pointing 180. The magnitude stays the same the whole time, and it's very important to remember. This will all make sense in a few minutes. We'll do a couple example problems, and we'll see exactly what we mean by adding and resultants and all the things. So we can draw them to add our vectors, and we can use rulers and measure things out, draw things to scale. It's nice, but the problem is you don't always get 100% accurate data. Answers what you get may not match someone else's, so that can be a little difficult. So another way we can do is with components. All right, components make life really easy. When we start to get into vectors that are at different angles, components are what are going to save us. Right? So components are projections of a vector onto the x and y axis of a coordinate plane. The nice thing, they're always perpendicular to each other, which again means that the x component will not affect the y component. All right, you want to think about components as little bits and pieces that when you put them together, they make a full vector of whatever it may be. And again, solving problems involving vectors is easier when we use components. All right, so let's say we want to do some vector addition. First way we talked about was drawing them out. If you have a certain equation, right, and seeing what they look like, draw that resultant. So the first thing we can do, let's say we have a couple vectors here. Let's see, can I get an arrow? No, I can't. How about right here? Oh, I got an arrow. All right, so let's say I have one vector, and it looks like this, okay? And then we'll get another arrow, and we'll call it something. We can go around. There we go. So we got these two arrows, right? Two vectors. We'll call them vector A and call them vector B. Now the important thing, you see this little like arrow thingies that I put on top of A and B. Those are symbols that denote that I'm dealing with a vector. In your book, sometimes they'll put arrows over the top of them. Sometimes they just put them in bold. All right, very important. So to think of them this way, vector on top, that arrow symbol on top, it's a vector. It has to have a magnitude and a direction. No, or if it's a bold, the same thing. No arrows, no bold. It is a scalar, so it has a magnitude only. All right, so let's say I take these two vectors, right, and I want to move them around a little bit. I want to add them up. I want to know what is A plus B equal to. Okay, so to get that done, well, I'm going to do it because it's A plus B. I'm going to move them around so that I can get them in the form of A and then B. All right, so if I take the move tool, I move it over, let's say, so we've got some space. We've got A right there, and then I'm going to take B and I'm going to add it tip to tail. So I'm going to take the tail of B, I'm going to add it right to the tail, the tip of A, and that's what A plus B looks like. But I want it to look the way, I want to know what that resultant is. I want to know what R is. So what I'm going to do is I'm going to draw it out, and that's our resultant R right there. All right, that's what we get when we add the two of them together. Okay, it's good for if you want to just get an idea of what things look like. This is a good method to draw it out, but again, it's not going to give you great results when you're trying to get good hard data to go with it. So let's say we take A and B again. All right, we'll just slide them over here for now, get them out of the way. And let's say now we want to find out about what is A minus B. All right, so when I do that, this changes, this guy changes, B changes. And what he does is he gets flipped around 180 degrees. Let me just get our roll resultant out of the way. He gets changed 180 degrees. So if I go here, right now, B, same length, more or less, just going in the opposite direction. All right, so A minus B, we'll take our A, tip to tail with B, and now our resultant, when we add the two of them together, looks like that. All right, and that is quite different. When you compare the two of them, just by adding them or subtracting them, you get quite a difference in what our results should be. So again, this works for all of them, any amount that you have. So if you have 10 vectors, you add them the same way. All you do, right, is just go from the tip of one to the tail of other. So you could have this, you could have another one like that, you could add another one over here, another one over here, and then find out that the resultant looks something like that. All right, so you can add them all up, get all kinds of different combinations, right? The goal, again, is to do tip to tail. And once you do tip to tail, you are good to go. All right. All right, so now we're going to look at the component method. Components a little better, a little nicer. They work a little bit easier for us, and this is the way we're going to deal with it probably about 100% of the time in class. So let's say we have this vector here. All right, we'll call this, again, we'll just call it vector A, make it nice and easy for us, right? And I want to know, what are its components? What are the building blocks? What are the pieces that make it up? So I'm going to take a couple of these vector guys right here, these arrows, right? And I'm going to have one vector that looks like this, right? And that's my x component, right? And then I'm going to have one that is my y component. And he's going to go up, oops, wrong, don't do that to me. I'm going to have one that goes like this, okay? And you're going to see they go along the x and y axis. All right, and you'll see that they're perpendicular to each other. They're always perpendicular to each other. They will never not be perpendicular to each other. We call this one a sub x, and we call this one a sub y. Okay, and now these are the two pieces that make up A. And the nice thing now is we can get rid of A. We don't have to deal with A anymore because we have the components. And you'll notice that a sub x goes from the tail of A, and it lines up directly underneath the tip of A. And you can see the same thing for Y, right? Starts at the tail of A, and it lines up directly with the tip of A. Okay, and we get it nice and easy. That's how we set them up. You guys did this in your sum work, so it should be a pretty quick and easy review for us. And what we can do if we makes life a little nice and easy, if we take this over here, we add them up, look, we've got a right triangle. And that is where it becomes important. Okay, that's at some angle. So if we look at this, we get a sub x and we have a sub y. A sub y is opposite our angle. So just by doing some right triangle trigonometry, we can find that a sub y is going to be equal to a sine theta, the magnitude, and that a sub x, oops, it's going to be equal to a cosine theta, because here's my adjacent side, right? Here's my hypotenuse, SOHCAHTOA, I get the cosines. Now if I want to find out what a is, because I have these two pieces right here, and I want to find a, right? A then becomes square root of a sub x squared plus this a sub y squared, which is just the Pythagorean theorem. And if I know these two pieces right here, I have the opposite and the adjacent, and I want to find this angle, that sounds like tangent to me, TOA. It ends up being that inverse tangent of theta is equal to a sub y over a sub x. These are all important. They're going to be really useful for you. Make sure that you keep these in the back of your mind. But of course, if you can just knock out that trig, right, if you know SOHCAHTOA, that's going to help you get through everything, and you'll be in really, really good shape. Okay? Now, all of this was nice, and it works great as long as you're assuming that you're on a nice, flat, horizontal surface. But we know that life is not always a nice, flat, horizontal surface. Sometimes we have to do things on hills. So if that's the case, we imagine our hill is like this, and we draw a little ramp kind of thing. That, and here's our angle. Okay. We want to see what happens to some sort of vector. Let's say the acceleration, right? Gravity is going to cause things to accelerate. What's going to happen there? So imagine we just have like a box. You guys will find out very soon that I'm horrible at drawing, so I make things as simple as I can. So boxes, circles. So the nice thing is gravity is always going to be straight down. So you see that I take it from the center of the object and I push it straight down. Now what I want to do now is I want to break that into components. And really what I'm doing is I am tilting the coordinate system is really what's happening. Right? I'm taking my coordinate system and I'm setting it, the x equal to the angle, the x-axis equal to the angle of the ramp. So when I do that, I guess I could draw it out. Yep, we get something that looks kind of like this. There's my x. And there's my y. So imagine, again, I'm just tilting my coordinate plane to be on the same angle as the ramp. So when I do this, I can look at you'll see that the gravity is not directly on the x or y axis, but my components can be. So if I draw my x component to look like this, right, g sub x. If I draw my y component, same way, I can draw it over here, right? I get my g sub y. And it works out nicely that this angle is the same angle as the angle of the ramp. You guys can knock out the geometry and figure that out for yourself, but that ends up what ends up happening. And you look here, things flip. The x component no longer uses cosine, it uses sine, because now g sub x is opposite our angle over here. So we get that, in this case, g sub x is equal to g sine theta, and g sub y is equal to g cosine theta. All right, and that ends up being, something very important. So typically, when we're on a ramp, the x component gets a sine, the y component gets the cosine. And then when we are not flipped, so we're in the normal coordinate system, the x component gets cosine, the y component gets sine. But something to pay attention to, that geometry is very important. All right, so keeping this in mind, let's go through a problem. I'm going to look at problem number 17 on page 97. So I'm on page 97, number 17, and it says, a car traveling at 30 meters per second runs out of gas while traveling up a 5-degree slope. How far will it coast before starting to roll back down? All right, so I know that 30 meters per second is the initial speed. And they tell us that it's got an angle of 5 degrees, right? That theta is 5 degrees. And they would like to know, how far does it travel? So I'm going to call that my delta x. And along the way, right before it starts to roll back, it has to stop. And that's when my final speed is going to be equal to 0. So it's always helpful. Draw a picture. Here's my awesome car, box car. We know that this is 5. And the only thing that's going to cause it to move is gravity. And we know that we're going to get gravity going this way. That's going to be my x component, and this is going to be my y component. And by looking at these two arrows, right, these two vectors, the gravity vectors, I can see that only the x component of gravity is going to cause it to move. All right, and we know that the car is traveling up the hill. All right, so again, the x component of gravity is the only thing that's going to cause it to move. And again, I want to know delta x. I'm going to go with, I believe they sometimes call it the third kinematic equation, which is v sub f squared minus v sub o squared equals 2a delta x. Plugging in what I know that we've got 0 squared minus 30 squared is equal to 2 minus g, because we're calling it minus g because gravity is going in the direction that is opposite the direction of motion. If the car was flowing down the hill, we would call it positive g, but because they're in opposite directions, we're going to call it minus. So we get minus g times sine of 5, that's our angle, times delta x. Okay, so we get minus 900 squared equals minus 18.6 sine of 5 delta x. The minuses are going to cancel out. All right, I get 18.6. 2 times 9.8 gives me 18.6. All right, so if we figure out what this is, do 900. Sorry, that's not 900 squared. What am I doing? Divide it out. We should get that delta x is going to end up being about 525 meters. And that's that. All right. A lot of work to do. Some of it's a review, but it's a really good application in terms of getting where we need to get to solve some pretty complex problems when we start shooting things from different places and we want to know where they end up going. We need to know how to manipulate vectors, and we need to know how to then solve them to get where we want to get. So that's it. I hope you enjoyed it, and we'll see you in class next time.